All right, so I want to look at an interesting question here. We're going to look at differentiation and integration and its application to that in a box. So we have this cube here, right? And this cube, right, all has equal sides. So we're going to have this, we'll call this L, call this L, and we'll call this L, right? So it's all equal, it's a cube. So we're going to find that the volume of cube we know is L cubed, right? If we times this dimension by this, we'll get area. If we times, so we have this area here. If we times that by this length, we're going to get the entire volume. So what is the derivative, though, of this? What does that give us? So let's take d over dl, right? Because with respect to the length of L cubed. What will that give us? What does that mean? That will give us, right, from the power rule, so that's n minus 1, right, times n. So that would give us, well, if we take n, that's 3, n is equal to 3, and then we subtract n minus 1, well, that's 2. For completeness, we'll do it out. Oops, I did, that should be a 1 right there. That will be 3L squared. So what does that mean? Well, it means we have L squared plus L squared plus L squared, and that will equal 3L squared. So a differential amount of the volume is equal to 3L squared. Let's think about that on the box picture. So I'm going to do this in green so you can see it different. So that means really we have, well, this is an area. This is area, right, of one side of the box, L times L. So let's, highlight that. Here we go. That's another area, right? So we have here. And then we have another area here. So a differential amount of a cube would be this. So we can think about this as also as taking these components off, right? Taking this thing off the top where this is L and this is L, and then we can do it over here. This is L and this is L. It's a horrible line over there. I'm sorry about that. And then we can take it off here. I'm going to try to draw this best I can. That's really, that should be more cubish, right? So we see that this thickness, right? How thick is an area, right? Well, the area is not really, it has no thickness. And that really is what a derivative is. It's some amount of really nothing. So basically, if we take this derivative, we have 3, we know it's 3L squared, and we integrate it, right, to get the volume of this differential amount. We get 3L squared dL. Integrate that, we're going to get 3, in fact, out of 3, L squared dL. That will give us 3. And then from the integration power rule, we know that it's going to be x. Well, we're going to subtract 1, so we're going to add 1. And then, well, we brought that down before we subtracted. So to find the original one, because we have the n minus 1 on the top, we must do n plus 1. So we're going to get x. Well, in this case, it's L. Oops. L. 2 plus 1 for 2 plus 1. That will give us, that's going to be 3. So that's going to cancel out with this L cubed. And that gives us the volume. So having a differential amount of 3L squared, right? Differential amount of all these will give us this cube back. It's just a really interesting way of looking at derivatives and integrals in a box application. If you have any questions or comments, please let me know in the comments. All right, that's all for today.